Hello everyone, today we're going to be going over the 35s. The new thing that we're going to be adding today is this step into your problems. Right down here I said we're going to talk about STP conditions. They're found on the back of your periodic table, and I'll show you where those are as we are going along. So we're first going to do a little bit of math up here. It's not going to be too strenuous on us. So name of the gas, the symbol for helium is a capital H lowercase e. It tells us how many moles we have. It tells us how many grams we have. It tells us how many liters we have. So over here it wants us to calculate the molar mass. So I would just simply take the grams and divide it by the moles. And that's how we get molar mass. And if we do that math with the correct sig figs, we get 4.00 grams per mole. And if you find helium on the periodic table, that is exactly the molar mass of helium. So just showing us that we can find the molar mass that way. But now we're going to look at something called molar volume, which is liters divided by moles. So that gas took up 2.49 liters according to this. And how many moles do we have? That's how many moles we have. So we're going to divide that by the 0.111 moles. We do that math and we end up getting 22.4 liters per mole. And that is how much space, how many liters 1 mole of that gas would occupy at certain conditions. And we'll talk about those certain conditions as we're going along. So let's do that for another gas. We got argon. And the symbol for argon is capital A lowercase r. It gives us the information right here. We do the grams per mole, 1.33 grams. Or excuse me, that's 133 grams. Let me just erase that real quick. 133 grams. And how many moles do we have? 3.33 moles. And if you do that, you get 39.94 grams per mole. And if you look that up on the periodic table for argon, that's exactly its molar mass. So now let's do its molar volume. So that's liters divided by moles. So I got 74.6 liters. And I'm going to divide that by moles, 3.33 moles. And when I do that, I get 22.4 liters per mole. And again, that's how many liters 1 mole of that gas would occupy. So if we look at this, we got 22.4 there, 22.4 there. And the idea that we're trying to get across is it does not matter what gas we are talking about. It will occupy 22.4 liters of space if you have 1 mole of gas under certain conditions. And we will talk about those certain conditions starting on the next slide. So it says, under what conditions would a gas fill 22.4 liters? So first of all, let me start off with, this is roughly the size of 22.4 liters. So 1 mole of gas would occupy this container under certain conditions, and it's wondering what those certain conditions actually are. So these are standard temperature pressure conditions. So the pressure must be gas, first of all, to occupy that volume. That's the first thing that we need it to be. The temperature must be 273.15 Kelvin. So that's a nice number that we've been using as we've been going along in this unit. And the pressure must either be at 760 millimeters of mercury or its equivalent, which is 1 atmosphere. Again, these are equal to each other, so at either of those, that would be perfectly fine. So those are 3 conditions that this many liters would be 1 mole of gas. So I want you to go to your cover at this point in time, and we're going to notice that we're going to be looking at a few of these things. So we will definitely be going between moles of one item and moles of another. We use the coefficients in a balanced equation. We're going to be going between grams and moles. So we're going to be using the molar mass off the periodic table. We'll be going between atoms and molecules, 2 moles. And we'll be using that 6.02 times 10 to the 23rd. And we're going to be using moles to liters a lot. And that's when we're going to be using this number and we're going to be having to be at STP conditions, which is that 760 millimeters of mercury or 1 atmosphere, and the temperature would have to be 273.15, and I'll show you where that is on your periodic table as well. So on the back of your periodic table, this was our last unit, the standard reduction potentials, and right next to it, it says standard temperature pressure conditions, STP conditions. It tells us the pressures and it tells us the temperature, so that's right there for us. It also gives us the number of 22.4 liters is 1 mole of gas, and just in case you forgot it, 6.02 times 10 to the 23rd of anything is 1 mole of whatever that anything is. So those are some things that we'll be using as we're going along. So here's our first question. It says a 22.4 liter box will contain 6.02 times 10 to the 23rd atoms or molecules of gas at standard temperature and pressure. Some gases are atoms, so like helium, and some gases are molecules like H2. So that's what it's trying to get at. So how many molecules of helium would there be in a box, in a 22.4 liter box at STP? Well, this is the size of the box. We're at standard temperature and pressure, and it wouldn't matter any gas in a 22.4 liter box at STP conditions would be 1 mole of that gas. If I had 6.02 times 10 to the 23rd molecules of nitrogen, that's 1 mole of nitrogen gas. How big a volume would that be at standard temperature and pressure? Well, that'd be 22.4 liters. That's how much gas would be occupied by 1 mole of gas molecules or atoms at standard temperature and pressure. 22.4 liters is the volume of 1 mole of O2 at standard temperature and pressure. D, if the volume of 1 mole of oxygen and the 1 mole of nitrogen is 22.4 liters at STP, then the acronym EVEN is true. EVEN says equal volumes of gas have equal numbers, and we have to add a little bit to that. Equal volumes of gas at the same conditions will have equal numbers of atoms of molecules of gas. So let me give you an example. Let's pretend we got 2 different gases here. Let's say we got hydrogen gas in this one, we got oxygen gas in this one. If both of these flasks are under the exact same conditions, they will hold the exact same numbers of particles inside. And particles, I mean either atoms or molecules. So as long as the containers are the same size, the conditions are the same, then they will have equal numbers of molecules inside of them. That is what EVEN stands for. Equal volumes, equal numbers, as long as they're under the same conditions. We're going to be using that principle a lot. So here I have 3 different balloons. I have 1 mole of helium, I have 1 mole of ammonia, and I have 1 mole of oxygen gas in there. If we look at these and they're all under the same conditions, the EVEN principle will work. They'll have the same number of molecules. And this has 9 atoms in that one. This has 9 molecules, and this has 9 molecules. So EVEN, equal volumes, equal numbers. Equal volumes under the same conditions have equal numbers of particles. And particles, I'm talking about molecules or atoms. So we're going to go through some true-false questions. I'd like you to definitely pause the video, see if you can answer the question first, and then see if you are correct. So there are many types of this question on the test, and this is important for you to understand. So it's kind of a rapid-fire way of seeing if you understand topics, but you really do need to think about it as we're going along. So here we got a box and a box. Let's say they're sealed boxes, and this one's got nitrogen gas in it, and this one's got oxygen gas. And if we look, that one's at 2 liters, and that one's at 2 liters. And this one's at 700 millimeters of mercury, and this one's at 700 millimeters of mercury. And this one's at 27 degrees Celsius, and this one's at 27 degrees Celsius. So the only thing that's different between these two is the actual gases that are in the box. So the question is, each box above contains the same number of molecules, true or false? Pause the video, see if you can answer that. Well, the conditions are the same between these 2 boxes. So if the conditions are the same between these two boxes, and both of these are gases, the even principle is true. So this is true. Each box has the same number of particles because they're under the same conditions. And the reason for that is the equal volumes of gas at the same conditions will have the same number of molecules of gas. This is known as the even principle. All right, try the next one. Each box above contains the same number of moles. Well, that's true as well. If they have the same number of particles inside, then they would also have the same number of moles, because you can go between atoms to mole island without any problem. And again, that is the even principle. Each box has the same mass of gas. So pause the video, see if you think that's true or false. The answer is false. So let's say this was 1 mole, and let's say this was 1 mole. Well, 1 mole of oxygen is 32.00 grams per mole, and 1 mole of nitrogen is 28.0000 grams per mole. So no, they would not have the same mass because they have different molar masses. On average, molecules in A are moving faster than B. So we talked about this a couple weeks ago, kind of associated with a motorcycle and a dump truck. Which moves faster? Well, a motorcycle can move much faster because it's much smaller. So smaller molecules move faster, larger molecules move slower if they're at the same conditions. So on average, molecules in A are moving faster. These have less mass at 28 than the oxygens at 32, so they would be moving faster, and that would be true. So again, we talked about kinetic energy a while ago. For them to have the same kinetic energy, so they're at the same temperature, the same kinetic energy, if one has more mass, then it must move slower. Its velocity must be less, and vice versa for the one that is lighter. Again, we talked about that several weeks ago. All right, so here we go. How many molecules of chlorine are in 88.88 liters at STP? And it says you have to state that you're at STP every time you use 22.4 liters in a problem. So let's go ahead and solve this. 88.88 liters of chlorine. So that's chlorine gas. And we are at STP. So we got liters there, and we can go 22.4 liters is 1 mole of Cl2. And we write at STP because it tells us the conditions we are in the problem. The only time you can use this step is if you are at STP, and you must state that you are at STP when you solve it. So if we do the math on this particular problem, we end up getting 3.97 moles of chlorine gas. So we just found a way to go between liter island and mole island on the cover of your unit pack. So there's a prettier version. And again, we just went from liter island on your cover. We went up to mole island, and we used 22.4 liters equals 1 mole, or per 1 mole, to go between these two. But again, you must be at STP conditions, and those are on the back of the periodic table if you forgot those. All right, so now we're going to go a little bit further with these problems. So we look at this problem, you have 777 liters of neon gas, you have the pressure, you have the temperature. What is the volume at STP? So it wants us to find the volume. So I'm going to start off with the volume. Whatever I'm trying to find out, I'm going to start off with. So liters of neon gas. Multiplication sign, division bar. I am at 750 millimeters of mercury. So I go 750 millimeters of mercury, and I am going to STP conditions. So it's 760 millimeters of mercury. So that's where I'm going. So my pressure is going up. Pressure and volume are inversely related, so your volume goes down. So I need to arrange these two numbers to make this volume get smaller. So if I want my answer to get smaller, I put the smaller of the two numbers on top. All right. Now let's do the temperature one. I'll do that in a different color. So our temperature here, we are at 255.4 Kelvin, and standard temperature is 273.15. So my temperature is going down. If my temperature goes down, my volume needs to go down. Those are directly related to each other. So I need my volume. Oh, I screwed that one up. Sorry about that, folks. Misread that one. My temperature in this problem is going up. If I want my temperature to go up, my volume would also go up. All right, so now I want my volume to get larger according to this, so I put the larger of the two numbers on top. 273.15 Kelvin and 255.4 Kelvin. Okay, and I'm going to crunch those numbers. And when I crunch those numbers, I get an answer of 820. And to get the correct sig figs, I got to put a decimal point there, and that's going to be liters. So the K's cancel out, the millimeters of mercury cancel out. We're left with our label in liters, and that's how we would go about doing that problem. There's a prettier version of everything that I just did right there for you. Remember to have this step and this step. We find students that make all kinds of mistakes if you don't include these steps in the problems that they are doing. G2 says true or false, 777 liters of neon gas at 750 millimeters of mercury and 255.4 Kelvin will be a different volume at STP. Well, that answer is true. Okay, that is absolutely true. So we have this volume at the conditions in the problem, and we have this volume at STP. So if you change the conditions, you will change the volume of your gas. All right, so the next problem, it says you have 777 liters of neon gas at 750, 255. Okay, how many moles of neon do you have? Well, this is all the work. We did this work already. We went to STP conditions. We did all that work already. So that is everything up to here, okay? That's everything that we have done already. So we're at STP, and now we can do a conversion from liters, which are right there, and liters go down here, and we can go to moles because we are at STP conditions. So we crunch the numbers, and we end up getting an answer of 36.6 moles. So this was a problem where we just baby stepped you through everything as we were going along. Pause the video, write that down if you need to do so. Again, we took these liters right here. We did some conversions. We got it to STP conditions. Now we can use this, and we can go to moles. When will 22.4 liters of a gas have 6.02 times 10 to the 23rd atoms of a gas or gas molecules? Well, that's under standard temperature and pressure, STP conditions. Again, standard pressure is 760 millimeters of mercury, or 1 atmosphere of pressure, and standard temperature is the 273.15 Kelvin. So those are your conditions. Those are also found on the back of your periodic table if you would ever forget them. All right, can I use 1 mole of gas to fill up a 22.4 liter container at any temperature other than 273.15 or an equivalent temperature? And the answer is no. You need to be at standard temperature and pressure to fill this container to 22.4 liters. Higher temperature, it's going to occupy more space. Less temperature, it's going to occupy less space. Just the way that it goes. Can you use 1 mole of gas to fill up a 22.4 liter container at any pressure other than 760 or 1 atmosphere? And again, the answer is no. It's always got to be those temperatures and pressures for that 22.4 liters to be correct. If you add more external pressure, it's going to occupy a smaller volume. If you have a less external pressure, then it's going to occupy a larger volume. So no, you need those conditions for that to occur. So in this problem, it says we have 20.3 grams of neon at STP. What volume will it occupy? So we're here on gram island. We're going to have to go over to mole island, and then we're going to have to go down to liter island to get our answers in order to solve this problem. So again, we have the 20.3 grams of neon at STP. What volume of gas will that occupy at 0.92 atmospheres and 255.4 Kelvin? All right, so here we go. We're going to start this problem out with our 20.33 grams of neon. Can't really do anything with grams, so we're going to convert those grams to moles to go to mole island. So we've got that set up. If you want to put the molar mass in right away, that's 20.18 grams is 1 mole of neon. So now we're at moles. It says we are at STP condition, so we can use that 22.4 step. So 1 mole is 22.4 liters of neon. And we have to write we're at STP because we are, in fact, at STP. It told us that in the problem. So we're at STP conditions. We got it to liters. And now we're going to have to go to the conditions in the problem to find out the liters at the end. All right. So now we are at STP. So we are at 1 atmosphere. And we are going to have to go to 0.92 atmospheres. So our pressure is going down. So that our volume should go up. Our external pressure went down, so our internal volume will go up. So you want to arrange these two numbers to make sure that this number gets bigger. So we put the bigger of the two numbers on top, 1.00 atmospheres. And 0.92 atmospheres. All right. Now we're going to go down a little bit. Kind of ran out of some room, so I'm going to have to be creative. So we are going to be going from standard temperature, which is the 273. So 273.15 Kelvin. And we are going to be going to the problem temperature, which is 255.4 Kelvin. So in this problem, our temperature is going down. If our temperature goes down, our volume should go down. So our volume should get smaller. So you put the smaller of the two numbers on top. 255.4 Kelvin, 273.15 Kelvin. If you crunch all those numbers, and you want to look at a prettier version of all that, you end up getting 23 liters at the end. So again, there's a prettier version of it. You can see what we did. So we started off over on this side. We went grams to moles. We did moles to liters because we were at STP. We went from STP conditions to the conditions in the problem. We did those conversions, and we ended up getting the liters at the end. Pause the video if you need to take some time to take all of that in. All right, so here's our next problem. We have this many atoms of neon. How many liters of neon will you have at this temperature and at that pressure? So again, we have atoms, so we're going to be having to go to moles, and then we're going to have to go down to liters at the end. So those are the atoms that we have, and we are at STP, and it wants to know how many liters of neon gas would we have at these conditions in the problem. So we start off with the atoms, 7.654 times 10 to the 25th atoms of neon. Multiplication sign, division bar, atoms, neon. If you're on atom island, the only place you go is to mole island, so it's moles of neon. The number 6.02 times 10 to the 23rd is used there. There'd be 6.02 times 10 to the 23rd atoms in 1 mole of neon. It said these atoms are at STP, so moles are on top. I can go moles on the bottom, and I can go liters of neon on top. We are at STP, so there's 22.4 liters in 1 mole. So we are at STP conditions, and we're going to go to the conditions in the problem. All right, so here we go. Change colors just so it's a little bit easier to see. We're going to be going from standard temperature to the temperature that they give us in the problem. So we're going to be going from 273.15, and we're going to be going to 299.99 Kelvin. Our temperature is going up. If our temperature goes up, our volume should go up. So if I want my volume to get bigger, I put the bigger of the two numbers on top. So I get 290, oh, excuse me, not 2.9, 299.99 Kelvin, 273.15 Kelvin. Multiplication sign. Pick a different color. So again, when we use this, we are at STP, and that is 1 atmosphere. So we're going to be going from 1 atmosphere to 0.991 atmospheres. So our pressure is going down. That's our external pressure is going down. So our internal volume should go up. So I want my answer to get bigger. So I put the bigger of the two numbers on top, 1.00 atmospheres and 0.991 atmospheres. I crunch all of those numbers, and in a prettier version, I end up getting the answer of 3,160, or if I want to do it with sig figs and scientific notation, I can get 3.16 times 10 to the third. So again, pause the video to write stuff down, to soak it all in, to make sure you understand what's going on, because this is the new type of problems that you're being involved with. The whole thing that's new is this step right here. That's what's new. And the rest is your homework. So have a good day.